This, I still can't get used to the creepy robot saying something different this time. I guess they changed it at the turn of the month. This Zoom session is being brought to you by the fractal snowflake curve. I bet you can hear that cat. Anyhow, today we finish off chapter 4 with a very short section. One of those ones where we, excuse me, I was throwing a cat treat out the door for the cat to chase. This is about simple and damped harmonic motion. Now, this is one of those topics where they could, skip it, or they could write a whole book about that one thing entirely, but here they do very, very briefly. Okay, the idea is the weight on a spring, and you pull it away from its resting position, and it goes boing, oing, 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 oing. All right, fine. It makes a wave-like motion. Because ultimately the force of the force of restoral is opposite and proportional to the distance displaced. So this tends to make a particular differential equation, which causes the sinusoidal motion. Okay, fine. If d is the height or displacement from equilibrium and t is time, then d will be a cosine omega t or a sine omega t, or maybe some phase shift, whatever. And a is the amplitude, as you might expect. The period is 2 pi over omega. Its reciprocal omega over 2 pi is f, the frequency, in radians per second. So for example, here we have d equals 5 sine 3t. What's amplitude, period, and frequency? The amplitude is 5. The wave looks like this. This period is 2 pi divided by this 3. The frequency is the reciprocal, 3 over 2 pi. All very elementary, and the problems assigned there in the book is pretty much this. There's also a little more complicated thing, which, well, really the only proper way for us to do it is with a calculator or some other technology. And that's damped vibration. We have a weight in a spring, but there's friction which slows it down. So it starts out by wobbling, but the wobble dies out. And this can be thought of as being underneath an decaying exponential curve. So it's a sinusoidal motion times a decaying exponential, a e to the minus kt cosine omega t. And all right, and this too derives from a differential equation, but the derivation is a little more complicated, and besides, it's all in the calculus. You haven't gone to that yet. And the graph is a pain in the neck. Like I say, really the best way to graph something like, say, this would be to use a calculator. So here, d equals e to the minus t over 2 pi cosine t. What's its graph? Well, it looks like this. It starts off as a wave which gradually dies out. So okay, really that's the topic of this material, of this section. There's, like I say, there could be none, there could be a lot more, but the book decided to compromise with a small amount of this. So they'll ask you in the homework to graph and find some simple harmonic things, find amplitude, period, frequency in the graph. And they'll ask you to graph the damped vibration. And for that, you'll need to have access to some kind of graphing facilities. So, okay, that's it for it. Let's turn it off for now.